session. Here we go. Okay, so 10.2 talks about series. Do you guys have questions on 10.1? Any of the problems? Taking limits, divergent sequences. Okay. Well, one thing I want to mention is that I have a. Oh, you have one, Alex. Go ahead. I was gonna say that I'm not gonna be able to hold office hours right after this ends at 11. So, but I'll be able to help tomorrow. Wednesday we have no class, but at 11 you're welcome. Join the meeting. I'll keep it open for you guys. Ask you. But Alex, go ahead. The one that is separated by vectors. Well, you just have to do it component wise. So let's say you have a vector which has 3 components: A sub n, B sub n, and C sub n. And this is simply take limit of each component separately. But the thing is, if one of them diverges, the whole thing diverges. The whole vector diverges. In fact, this converges. It converges if all components if one of them diverges, then the vector diverges. You might have, a vector of 1 over 2 and 1 over 3 to the n, n over n plus 1, and comma negative 1 to the n. This one converges to 0, converges to 0, converges to 1. That one diverges. The limit doesn't exist, right? For that reason, the whole vector diverges. Does that answer your question? Okay. Any other questions? All right. So we are going to talk about series. So remember yesterday we talked about sequence, okay, which was A1 comma A2, A10. This goes forever. And then we want to see what it converges to. What it converges to. I mean, does it even converge? If it converges, what it converges to. Or it doesn't converge or diverge. Okay. Now, series is an object built by a sequence. A series basically is the sum of all elements or terms, sum of all terms of a sequence. So basically, go ahead and add all those terms. There are infinitely many of them, right? And this is a series. All right. Now, it's very silly to write this down every single time. So for that reason, we come up with a notation called sum sigma a sub n, and n is starting from the first index, in this case 1, going all the way to infinity. So this symbol is the sum of a sub n from 1 to n. Okay, that's the notation. So when I say, when I say sum of 1 over 2 to the n, and it's starting, and n could start from any number, it could start from 0. You barely see sums starting from negative indices, start from -1. The most common case is n from 0, but sometimes you get a 0 in the denominator, so it's undefined. You see n start from 1, or there are cases n start from. And later we'll see it doesn't matter what series starts from. Like, it doesn't change the value of the series. I mean, not the value. Of course, it changes. It doesn't change the convergency or divergency of series. Okay. So let's, expand this basically. Write down term. So when starting from 0, the first term is 1 over 2 to the 0, right? Second one is 1 over 2 to the first. Second. Let's write down this one. So on. And as you can see, it's 1 plus, half, 1/4, 1/8, 60. And you can see the pattern, right? Each term is previous one multiplied by half. Starting from 1. In fact, this type of series has a specific name. We'll discuss it later. This is called the geometric series. Okay. Here's another one. Sum of n over n plus 1. Okay. N is starting from, like here, if you start from 0, nothing happens, right? There's no number making, the only number making denominator 0 is negative, but we don't have to start from, so we can start from 0. And it's 0 over 1 plus 1 over 2, 2/3, 3/4. And you can see the pattern. Numerator is 1 less than denominator. Excuse me. Okay. Let's write down another one. Let's write down the -1 to the n. Start from here. So that's -1 to the 0, -1 to the first, plus -1 to the second, and so on. As you can see, it's 0. It's 1 minus 1, plus 1 minus 1, plus 1 minus 1, plus 1, plus 1. Right? All right. And there are so many more examples that I can mention here, but don't have. Now, what's a big question asked about series? Same thing as sequence. Do they converge or diverge? Like, does this sum converge or diverge? Let me specify, emphasize, or, say something about the difference between a sequence convergency and divergence. A sequence A sub n could converge, but the sum of A sub n started from 0 to infinity, diverges. Right? In fact, there are there are many cases. So what I'm trying to say is that there are so many sequences that the sequence itself converges, but when you sum it up, the sum doesn't converge. We'll come up with examples. Like one example is this guy, the one that I have right here, the second one, so number 2. Like the sequence itself, the n over n plus 1 alone, not the sum. That one itself converges, and it does converge to, what does the sequence itself, what does n over n plus 1? Guys? 1. Exactly. Take limit. It's 1. But the sum of all those elements, the sum of those elements doesn't converge. In fact, it diverges. It diverges to infinity. Okay? The first one, on a numbered 1, that one is the case, not only the sequence converges, but the sum of all those guys also converge. Okay? We'll talk about them one by one. But here's a note that I wanted to make. So let me write down an example. N over n plus 1 converges, but sum of n over n plus 1 is starting from, let's start from 1 to diverges. But you're going to ask question why. We answered, 2 minutes. Okay. Let me see. Let me define something here that is going to make our job easy. So we have the, series A1 plus A2 plus A3 plus A sub 4 and so on. Okay. Which notation wise sum of A sub n n star. Now, the sum of first n terms, I mean, somewhere along the line here you have, A sub n maybe, let me use capital N, and so on, right? The next one is going to be A sub n plus 1. The first n terms, so the sum of first, and n is just a general, number that I'm using. So it could be first 10 terms, first 20 terms, first 100 terms. The first n terms is called the partial sum. It makes sense, you're summing part of the series, like the first few terms of the series, and that's partial sum. And let me use the station on the other side. I want to go to the next column. Okay. So S sub n, I'm going to call it A1 plus A2 plus, and the last term A sub n. Let me write the whole series again. Okay, so A1 by itself is basically S1, right? S1 is A1. The first two together is S2. It's the previous one. A1 plus A2. S3 is, A1 plus A2 plus A3, and so on. The nice thing about this is that we can look at this series, right, as a limit of the sequence. The new, basically, this is a new sequence, right? That's also so that S sub n is itself a sequence, right? Okay. Now, so wherever convenient from now on, we're going to use S sub n, and the limit of S sub n as the limit of the series or the value of the series. And here's the reason. An, and starting from 1 to infinity, I can go ahead and write it as, limit. So n from 1 to, instead of infinity, I'm going to use the letter capital N, right? So that's the sum of a sub n starting from 1 to n. And then I can take limit of that as n approaches to infinity. But this sum, we just defined it as what? That's basically the sum of the first n terms, right? This is nothing but a1 plus a2 plus a3 all the way to, but here you have an n term. The n term is a sub n. So I can go ahead and write it. That's limit of Sn going to infinity. Hopefully I didn't, confuse you with all the notations that I wrote, but my point was that, I can write an infinite sum as a limit of a sequence. That was the point that I wanted to make. Okay. All right. Now let's begin. Let's do our first theorem. Oh, let me define the convergence. Definition. We say sum of an and from 1 to converges if, if the sequence, the partial sum sequence S sub n converges. And diverges, same thing. That diverges, so diverges. That partial sum. All right. Here comes the first theorem. Let Sn be the sum of an n from 1 to capital. If the sum of an n from 1 to infinity, if this series, so series, converges, then the limit of an, the limit, of the term, of the nth term of the sequence, of the series, sorry, is 0. And this is a very useful theorem, okay, to recognize the series, if they converge or if they diverge. People keep going in and it's long. Okay, let's prove this. First of all, let me explain what it means. Basically, it means, let's say you have a series, okay? And you have the a sub n here, and you're taking sum of that. Let me just write it. And from 1 to infinity. If this series, so you know the sum of the value of this series is a finite value. When you say converges, it converges to some finite value. So this sum converges to some finite value. Okay? It has a limit. If this happens, you can say 100% confident that the an itself, so let me say then an itself has to approach 0. In fact, it does approach 0. So you can say that confidently 100%. Okay? No, let's prove it. And then we'll continue. So, we'll write y, we proof of theorem. It's very simple. Start with S sub n, the partial sum. Isn't it a1 plus a2 plus all the way to a sub n? But I'm going to write down the last two terms. One is a sub n minus 1, and the last one is a sub n. Right? Okay. I'm going to ask you guys a question, and then we'll continue. In terms of S, what's the sum of A1 and A2? What notation did we use for the sum of A1 and A2? It's S sub 2. Good. And if it's the first 3 terms, is S sub 3, right? First 4 terms is S sub 4. Now, what's the notation for the sum from A1 all the way through A sub n minus 1? What notation do we use for that? It's S sub n minus 1, right? So I can go ahead and write S sub n as S sub n minus 1, which is this part, plus A sub n. Right? And it's very clear. S sub 7 is S sub 6 plus the term A sub 7 that we adding to the previous, the last, the previous 6 terms summation. So let's go ahead and solve for A sub n. Algebra, it's going to become S sub n minus S sub n minus 1. Right? Now let's take limit. So limit of an as n goes to infinity is equal to the limit of S sub n minus S sub n, sorry, S sub n minus 1 and approaching it. The limit of sum, I can go ahead and write it as, let me go to next. Right. Let me draw a line, make columns. So we got to limit of A sub n and approaching infinity, it was limit of S sub n and approaching infinity minus limit of S sub n minus 1 as n approaches n. Okay. Maybe I should have, assumed something at the beginning. What do we know about the convergency of S sub n? S sub n was the sequence of partial sum. What was the assumption of the theorem about the S sub n? Which is the partial sum of the series we started off with. Sum of A sub n plus, it converges. Exactly, converges. Well, in terms of index, so we know this one converges, right? How about this one? I mean, that's the same sequence, right? Except the index is one less. But when n approaches infinity, there's no difference between n and n minus 1. Right? Subtracting a 1 from infinity is not going to do anything to infinity. So what about the sequence S sub n minus 1? Do you think that one converges too? Yes. Now, here's a question. Do they converge to the same value? Or they don't? No, but yes. What kind of answer is that? So a strong no, strong yes. Do both sequences converge to the same thing? I want to repeat it again. This n minus 1 is just an index. I can replace n minus 1 with m. If n approaches infinity, then m approaches infinity. And basically this term becomes limit of s sub m going to infinity. And my first term is limit of s sub n going to infinity. Now, let me ask again. Do they converge to the same thing? Yes. Both converge to the same exact value. And it's finite, right? So, what's the conclusion? What's the value of the right side? So it converges to S. Let's say, let me write it this way. Suppose S sub n converges to S by assumption. Then limit of A sub n approaching infinity is S minus S, which is 0. And that's what I want to show, right? I wanted to show that the limit of nth term of the sequence is 0. Any question on that? So let me write down the summary of the theorem again. If a from 1 to infinity or 0 to infinity converges, then an approaches 0. All right. Let me explain a little bit about this guy. This is a logical statement. Okay. Like I have it's called, P, then Q, So you do an assumption on P, and then that's the statement you want to basically prove Q. or something results in Q, right? P results in Q. Let me give you an example. And then I'll make my point. let's say I mean, these days you're not going out, but let's say you're let's do this one. I want to make it as simple as possible. You come home and you see your dad's car is outside, driving, okay? And it's a coupe, right? So if it rains, it's gonna mess it up. So you tell your dad, Dad, your car is on the driveway, and if it rains, it's gonna be a mess. You want to put it in the parking lot, or parking garage? And your dad says the following. It says, if it starts raining, I'll quickly go ahead and put it in the garage. Let me repeat it again. Dad says, if it starts raining, or if it rains, I'll go outside, put the car in the garage. So you go to your bedroom, you sleep. Early in the morning, you wake up, you go to the kitchen, and you look outside in the driveway, and you see your car's that outside, still in there. What do you conclude? Exactly, it didn't rain. So let me write it down. If it rains, car goes to garage. Now, what happened when you wake up in the morning? Car didn't go to garage. Conclusion, it didn't rain. So, these are both statements, logical statements. The second one is called the contrapositive of the first one. Okay? In fact, if the first one is P, then Q, what's the relationship between this one and this one? Like by grammar, what's the difference between car goes to garage and what car doesn't go to garage? They are opposite of each other. Exactly. And about these two, that's the same, right? It's the opposite of each other. So this car didn't go to garage, and logic is called the negation of this statement. So basically, our initial statement was P, like your dad says, if P happens, then I'll do Q. You wake up in the morning, you see Q didn't happen. Or you see Q not happening, you conclude, well, seems like P didn't happen either. So this is just a simple, don't worry about it. What I'm trying to say and the point I want to make from here is that the statement we have above was, finish this nicely. So if you have a statement P then Q, okay, this is equivalent to say not Q then not P. And you can see the relationship, right? If you have a PQ, then the negation of Q comes first, and it can conclude the negation of it. Okay. All right. Now, similar to that, I'm going to go ahead and write down the above statement. If sum of AN converges, we showed AN approaches 0. Now, can someone open the mic and tell me what the contrapositive of this statement is? So I'm going to write down the statement here. What's the contrapositive of this one? That I can write beneath. So what's the opposite of this guy?
If it goes to 0, then
this is already goes to 0. So what's the opposite of it? AN
if it
does
doesn't
not.
go to 0,
Yes. So if
then it diverges.
exactly. So this is the first important, conclusion or corollary that you wanted to make. In fact, this right here is called the nth term test, and it's a very powerful test to check to see if a series converges. Oh, it only helps you to see if the series diverges. It doesn't help you to see if the series converges or not. Like you can 100% tell if the series diverges or not. That's it. You can't tell if it converges or not. So that's called nth term test, and let me write it down. This test only helps us to judge if a series diverges or not. Remember, if a series, if you can't say it doesn't diverge, it doesn't mean right off the bat, that it converges. It might still diverge, but you don't know, by this test. You can only say if it diverges right off the bat or it doesn't. Okay? But it doesn't mean converges. Let me explain. In fact, I'm going to write down an example. Consider this sum. Let's do a few examples, just in the application of that nth term test. And I'll do a couple examples explaining if the opposite is true or not. So let's start with this. Do you remember we talked about this one? Sum of n over n plus 1, n from 1 to infinity. So here, a sub n is n over n plus 1. All right. What does an approach to? Approaches to 1. Is it 0? No. So we can go to this nth term test, because this test, this one right here, says if the nth term an doesn't go to 0, doesn't approach to 0, then what's the conclusion? The sum of an diverges. By nth term test, this is what you can write, by nth term test, since n over n plus 1 doesn't go to 0, then sum of n over n plus 1 diverges. Right? Here's another one. The one that we just talked about. Sum of negative 1 to the n over negative 1 to the n. And let's say from 0 to n. And we saw, it's 1 minus 1 plus 1 minus 1 plus 1 plus 1. And so on. And as you can see, every two terms, they cancel out each other. So you get 0 plus 0 plus 0 plus 0 plus 0. So it's sum of infinite 0. And what is the sum of infinite 0? I'm going to leave a question mark there. Because think about it. If I say it's 0, that means this sum is finite and it converges. Well, let's apply the nth term test and see if it converges or not. So what's a sub n here? A sub n is this guy. A sub n is negative 1 to the n. And what's the limit of an? As we talked about yesterday. The limit of negative 1 to the n and approaching infinity is waiting. Doesn't exist. Meaning it does not go to 0. I don't care. It doesn't go to 0. Since that doesn't go to 0, tells us by nth term test sum of negative 1 to the n, and from 1 to infinity or 0 to infinity diverges. Right? All right. Can you guys see the bottom of the page writing here? I should have go to the next page. I can just go. Here's another example. The sum of 1 over n and sum of 1 over n squared. So these are two different series. And started from, you can't do 0. Like this is one of the cases you can't start n from 0 because you get a 1 over. Okay. All right. So let's make the argument for this way. What is an here? An is 1 over n. And you take limit of that. What does it approach to? It goes to 0. So what's the conclusion about divergency and convergency about that guy? You asking me that? I need a response. I need an answer. I need a statement. You're asking a question. So either you say converges or diverges. Do you think converges? Diverges. Come on, guys. It's not a day of judgment. Converges, diverges. Of course, it's one of those cases, right? It's either diverges or converges. But at this point, you know what the best answer is? At this point, we say we don't. That's the answer. Remember, the nth term test only tells you, is only applied and only strongly you can make a statement if an doesn't go to 0. Right off the bat, you can say the city diverges. It's the same for this guy, right? It does go to 0. That means we don't know if it converges, diverges. However, later we'll see that sum of 1 over n from 1 to infinity, diverges. And interestingly, 1 over n squared n from 1 to infinity converges. So that's what we should be careful about using that nth term test, right? When it goes to 0, you can't strongly say it diverges or converges. In fact, when it goes to 0, that's where you're going to have to do a bunch of tests. Okay. Let me talk about one type of series that I wrote down as example, and I gave it a name, if you can recall, called it geometric series. Let's talk about that, and then, you know, we'll continue on Thursday. So, geometric series. In general, it has this form: a r to the n, and starting from 0 to infinity. Example: sum of 2 and then 1/3 to the n. Okay, sum of 3 and then 2 to the n. Sum of 4. Well, let's just write down 1/2 to the n. Like if you write down the first few terms of this guy, of course n started from 0. First few terms of this guy is 2, right? 2/3, 2/9, 2 over 27, and so on. First few terms of this guy is 3. 3 times 2 is 6. 3 times 4 is 12. 8 is 24, right? Each time you multiply by 2, you get the next. This one is 1 plus half plus quarter plus 1 over 8 plus, right? And here's the structure. Each term is the previous term by the same exact number. That number is called ratio. And this number in this setup is R. So R is the ratio, which is the ratio of 2 consecutive terms. For example, 12 divided by 24. Oops. So 24 divided by 12 is 2, right? 12 divided by 6 is 2. I'm assuming you have had something like this in high school. Not the series, but the sequence itself. So R is ratio, and of course A is called the first term. Okay. We're gonna go to over 4 or 5 minutes. Between these three, let's check something. Between these three, one of them for sure diverges. Which one is it? You can say left, right, first one, second one. Oh, someone said second one. Right. Why is that, Alex? That's because it grows exponentially. In fact, I mean, that's true. Yeah. You can see it's growing, right? Just keeps getting bigger and bigger. But you can also argue that by applying the n-term test. This is the a sub n. And the limit of a sub n is not 0. In fact, goes to infinity itself. Right? A sub n doesn't go to 0. So it diverges by n term. All right. But it seems like the other two might converge. Because the ratio is like over 1. I like that statement. It's a very good statement. That's a very good observation. The ratio is over 1, so it's growing, right? It doesn't increase. Because in the other two, if you look at the terms, like you go from 1/2 to 1/4, so the terms getting smaller and smaller. Whereas this one, the growth factor is bigger than 1. Terms are growing, which is the ratio. So it seems like it has something to do with these numbers, like ratio. Comparing it to 1, it's like bigger than 1, then seems like diverges. But let's see if it converges for ratio less than 1. All right, let's do some algebra. So this is what you guys can check later. If you have 1 minus x and you multiply it by 1 plus x squared plus x cubed plus, let's say, x to the n, then it is crazy. I mean, if you distribute it, you see it's going to be 1 minus x to the n plus 1. That's crazy, right? Like you have what? Here you have n plus 1 terms multiplied by 2, so there are 2n plus 2 terms, and 2n of them cancel out with each other. Like let's say if n was 10, you would have 22 terms. 20 of them would cancel out, and you're left with 2, which is 1 minus x. So you can check that later. Check on your own. So I'm going to go ahead and solve for this guy, which becomes, 1 minus x to the n plus 1 over 1 minus x. Okay. Now we're going to be using this. All right. So sum of a r to the n starting from 0 to infinity equals limit of a r to the n started from 1 to capital N using partial sum, then n approaching infinity. Now if you can see, we can write this as, a plus ar squared plus the last one is ar capital raised to capital N, right? So that's the limit of a is a common factor. I can pull it out. Then it's 1 plus r to capital N. And I can go ahead and use the argument we made above, and raised to infinity. So it becomes limit of a times 1 minus r to the n plus 1 over 1 minus r, and approaching infinity. Okay? So that's basically the limit of the series. Now, here, I'm going to make two arguments, or two cases. Case 1, if r is a value for which this guy is bigger than or equal 1. Right? And the other case is if absolute value of R is strictly less than. Question for you. What's the limit of, if R is a number for which absolute value of R is strictly bigger than or equal 1, limit of R to the n, or n plus 1, as n goes to infinity. You know what? Let's even split that one up to 2 cases. So I'm going to go ahead and split this one to, let's say 3 cases. So absolute value of R is strictly bigger than 1. R equal 1, R equal minus 1. And then one by one, you guys tell me. So what's the limit of R raised to n plus 1 as n goes to infinity? What's that limit? Remember, R is 1. The base is 1, you're raising it to some number, and then that number goes to infinity. The limit is 1. I mean, think about it. Base is 1. 1 raised to anything is 1. And if it goes to infinity, it's still 1. Okay? But our point is that limit is not 0. And think about it. If that's 1, you get 1 minus. Down here, you have 0 that's undefined. Okay? How about the case when it's negative 1? We already talked about this multiple times. What is the limit of negative 1 to the n plus 1? N going to infinity. That one does not exist. That one probably is the easier one. What's the limit of R to the n plus 1 as n goes to infinity? This is the case when the absolute value of R is bigger than 1. For example, you can assume n is 2. R is 2. So what's the limit of 2 raised to infinity? That's infinity. And again, it's not 0. So for all 3 cases, in fact, for this case, the limit doesn't exist. So that's not the case of our interest. Okay? So we only continue arguing when R is strictly less than 1. The absolute value of R is strictly less than 1. Because in this case, the limit of R to the n plus 1 as n goes to infinity is you can assume R is half. So what's the limit of half raised to infinity? You know, half raised to the n and then go into. Let me write it down. So half raised to n is the same as 1 over 2 to the n. Now n is approaching infinity. The limit is 0. Good, Donovan. The limit is 0. And it doesn't matter what the R, even if R is 0.999999, you raise this to n approaching infinity, it's 0. You can try it in a calculator. Like raise 0.99999 to 1 million. And see, it goes to 0 so fast. Okay. Okay, so that's the case we want, because in the case of R strictly bigger than or equal 1, it's not going to help us. So that if absolute value of R is strictly less than 1, we have let's continue with this. Let's do it this way. So sum of AR to the n from 1, 0, 0 to infinity is. So that was this limit. Let's go back this one. If R is strictly less than 1, that term goes to 0. So our limit has no n. That means it's going to be A over 1 minus R. A over 1 minus R. And there you have it. And it's very simple to memorize, because that ratio is first term over 1 minus ratio. So let's go ahead and find the sum, of the two series that we wrote down above. I think one was the sum of 2 over 1/3 to the n and starting from 0 to infinity. So it's a geometric series. Next thing you check to see if the ratio is strictly less than 1. It is. So 1/3 less than 1. So that the sum is. What is the first term of this series? And when you plug 0, it's 2. 1 minus 1/3. And you can simplify. 2 over 2/3, which is 3. Right? And you can do the same thing with the other one. So let's stop right here. If you have questions, feel free to ask. Sorry for going over 15 minutes. Post notes on e-learning. Yeah, we say it converges. But more important than that is